All right, homework out, if you would, please. Books open to page 204. And you had two problems to do for homework last night, problems 13 and 14. Let's go and review some things that we were talking about recently. And Michael, by the way, has got his equations written out on a 3x5 card. Keep it in his pocket at all times of the day except for chapel or Bible class. Be studying over, okay, don't do it in other classes either, but it's readily available to study. You will not, of course, have that out on a quiz or test. Anyway, page 204.
It's a cover sheet.
Oh, it's a cover sheet now. Right. No. Not a bad strategy, right? Putting the equations on a card and studying there. We've been talking about the tendency of a body to resist a change in its rotary motion. What do we call that, class? Rotational inertia. Meaning if a body is spinning, it tends to keep on spinning. Or if a body ain't spinning, it tends to not spin unless acted upon by an outside torque. Good. An outside torque can change that. And we said there's two things that affect the rotational inertia of a body. Remember, plain old inertia really is only affected, class, by how much? It's easier for me to slide this along the counter than it would be to slide Kendall along the floor. Why?
Mass.
Really, the mass is the main thing. Now, of course, there's friction, I suppose, as well, but mass is the primary thing that affects inertia, right? Well, for rotational inertia, there's two things.
Mass and distribution.
Mass and distribution of the mass. So what's our basic equation for rotational inertia? I equals mr squared. We then said that an object tends to maintain its rotary motion unless an outside torque acts upon it. What is torque, Kendall? Why did we go from saying outside force to outside torque? Are they the same thing? Kind of, yeah, almost. There's just one little element of torque that makes it different from a force.
Is it the angular?
Audrey? Michael?
Spin.
Obviously, torque is what causes spin, yes. The radius. Remember, even with the lever, right? Technically what you have when you have that, remember that lever demonstration we did where we had the different weights on different sides? Well, the weights represented forces, but the radii, the distance from the pivot point, is what allowed a little bit of force really far from the pivot point to counteract a whole lot of force close to the pivot point. Really what you were looking at were torques, right? And so the force, the product of a force and its radius is torque, so that our equation for torque, Kendall, back to you, based on a definition, the product of an applied force and the radius of that force. It's like little Greek letters. You remember what it's called? Pre-cal students help? Tau. Okay, so try it again, Kendall.
Tau equals R, and then the alpha.
Class? F. Tau equals FR. This is the definition of torque. A force times a radius, right? So if you're, anything that you're trying to spin, the further out from the pivot point or the center of that rotation that you can get, greater force or greater radius means you don't have to apply as much force to get the same torque. Force times radius. Now there's another equation for torque that we call the law of torque. What's that equation, Michael?
I alpha.
Tau equals I alpha. That's the law of torque, and that describes how torque can accelerate. Remember, we said a body tends to keep doing what it's doing. It tends to keep spinning at the same rate, maintain its rotary motion. Well, if it changes its rotary motion, that changes its spin rate, that's acceleration, angular acceleration. And so the torque needed equals the angular acceleration that you want times the rotational inertia. We multiply the tendency to resist times the amount of change we want. That's going to be the torque. So we have two different equations for torque. We also said this, that if an object is spinning, right, and it will tend to maintain that spin, even if circumstances change. So we talked about, we didn't end up doing it with Kendall, talked about putting Kendall in a chair and spinning her around and around. I just don't want to messing the floor of the computer lab, so we won't do that. But we've talked about putting her in a chair and having her spin her around and around with her legs sticking out, and then have her pull her legs in, or maybe I thought about bringing some dumbbells from home and she could hold the dumbbells out in her arms and then spin her around and around and then pull them in. And notice how the chair spins faster, and then as she puts her arms back out, chair would slow down, though the chair would slow down anyway because of friction. But we can see that this angular momentum is conserved. How do we represent angular momentum, though? Anyone? What letter do we use for angular momentum? L, of all things, and L is equal to? I omega. He did it again. I omega. And we said that if there were no outside torques and as an object spins, angular momentum is going to be conserved. Well, that means that I omega will equal I omega. In situation 1, with the arms out and the feet out, she'll have a certain amount of angular momentum. Well, if there weren't outside torques, and there definitely are, because there's definitely a fair bit of friction at the pivot of those chairs, then arms in and feet in, she'll still have the same angular momentum. But with her arms in and her feet in, her net radius has decreased, so rotational inertia goes down. She has less rotational inertia with everything in tight. And if that's true, if you decrease rotational inertia, what's going to happen to the spin rate or the angular velocity class? It will go up, right? So they'll work inversely of each other. However, I said you don't actually have to know this, assuming mass doesn't change, right? Now, if Kendall not only pulls the masses in, but she actually drops the masses and pulls her arms in, then she's changing the mass as well, right? But assuming the mass remains constant, and for our problems, the mass will, I said we could edit this equation for what? This is an equation we needed for our homework last night. Audrey?
Is it M1, no, R1 W, or omega squared.
The R squared. Remember, I is mr squared?
Yeah.
So it's mr, so we just drop the mass off. So R1 squared omega 1 equals?
R2 squared omega 2.
And this was the equation I want you to know for conservation of angular momentum. Okay, that assumes the mass remains constant. Okay, maybe not always, but if we spin Kendall too fast and she, okay, well then that changed the mass, so we have to account for that, you know? Anyway, I don't know, my brain goes strange places. All right, let's get back to physics. We also said that as an object is spinning, it is moving. And if an object is moving, it has energy. What type of energy does an object have if it is moving? Kinetic energy, right? Energy of motion. If it's spinning, it specifically has what we call rotational kinetic energy. What's the equation for rotational kinetic energy, Kendall?
1/2
That's linear. 1/2 mv squared is linear kinetic energy, but if an object is just spinning, right? We walk by, we see a little top spinning on the table. Well, it has energy, but it's not going anywhere. It's just kind of sitting in its place spinning, so, or a CD spinning in a CD player.
I omega squared.
Good. The m gets replaced with I, and the v gets replaced with omega. So 1/2 I omega squared. Now, if an object is rolling, it is moving forward and it is spinning, so we have to account for both. And what was that equation for total kinetic energy of a rolling object, Michael?
1/2 mv squared plus 1/2 I omega squared.
And it's important to remember that the v and the omega are tied together. V, the linear class, equals angular times radius. Therefore, angular equals linear divided by radius. And generally speaking, if an object is rolling, it's easy to see its forward progression. Meters per second is pretty easy to track. That's easier to track than spin rate, frankly. So normally you'd be given a V, you would need to calculate the omega. By the way, this we said, remember, is the basic equation for rotational inertia. If the object in question has a different equation than this, it would be given to you. All right, and let's go and take a look at the homework problems now. Page 204, problem 13. Read that for us if you would, Audrey.
Hoop of radius 3.24 meters weighs 1,250 newtons. How much energy does the hoop have when it rolls along the horizontal floor so that its center of gravity has a speed of 0.0334 meters per second?
All right, so it's a rolling hoop, Okay, like a hula hoop or something rolling along the ground, except this is a 1,250 Newton hoop. So it's about a 300-pound hoop. And its radius is 3.24 meters. It's about 10 feet. It's a 20-foot, it's a 2-story hoop. Okay, so this is a runaway Ferris wheel, all right? We have a 2-story hoop that weighs 300 pounds that's rolling along the ground, crushing everything in its path. Wow. All right, it's great. Who comes up with these? All right, anyway, very, very large hoop. And it says, how much energy does it have? Well, if it's rolling along the ground, it has 2 forms of energy, class. First of all, it has linear kinetic energy, but it also has rotational kinetic energy or angular kinetic energy. So here's the equation we should have used. Did we use this equation? So it's just a matter of plugging in the numbers. The total kinetic energy is going to be 1/2 the mass. Wait a second. They're stinkers. They didn't give us the mass. What do we have to do?
Divide by 1.8.
And I would say we're going to need this number again later, so I would put this number in the memory of the calculator. 127.5 blah, blah, blah kilograms. All right, and then the velocity, the forward speed.
0.0334 meters per second.
That is really slow. So it's not necessarily crushing everything, it's just very, wow.
It's just starting.
I mean, 3 centimeters per second. Wow, that's really, okay, whatever, 0.0334 meters per second. Of course, that needs to be squared, right? 1/2 mv squared, that's what we should have plugged in. So far, so good? We all found the mass? Okay, now, plus 1/2 I omega squared. But it's a hoop. What is the rotational inertia equation for a hoop?
MR squared.
Oh, hey, we get the easy one, the mr squared. Now the nice thing is we already know the m. That's in memory 1, right? And the r, it tells us, is 3.24 meters. So we can simply take the memory value times 3.24 squared, and that'll give us, wow, that's a lot of rotational inertia. What is the rotational inertia of this hoop? It very much resists a change in its spin rate.
1,338.
I know 1,338.97, blah, blah, blah. I'm going to put this in memory 2. So there's my rotational inertia. And then we need the omega. Well, what's the equation for, or how do I find omega? Yeah, it's theta rad over t by definition, but I don't know a theta rad or a t. But I know the linear, and I need the angular.
Velocity divided by radius.
Divide the linear by the radius. So I'm going to take the 0.0334 and divide it by the 3.24 radius, and that gives me an angular velocity of
0.00338.
and that value needs to be squared. Now, I don't actually need a memory for this, though, which is nice because it's on the calculator now. So while it's here, I'm going to go ahead and square it, multiply by the memory 2, which is my I, and then divide all of that by 2, take half of that. And I get right here, all the rotation, it's very little rotational kinetic energy, very small. 0.0711, blah, blah, blah. I'm going to go and use my third memory for that number. Store 3. Now I'm going to come over here, and I'm going to take half of memory 1 times 0.0334 squared. So 0.5 times recall 1 times 0.0334 squared equals, I'm going to add recall 3, and that gives me, again, it's moving so slowly, very low kinetic energy. What is the kinetic energy of the hoop? Anyone? If you don't have it, then you should have been doing this along with me. It should be 0.1422 blah, 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 or rounded off. I think it's 3 sig figs in this problem. Yeah, so 0.142 joules. Very low energy. Again, if you're not getting these numbers, you should have been working it along with me here. Questions? By the way, do you notice how I don't try to plug it all in one big piece? I was like, I'm just going to take pieces in chunks, put memories where I need them. Make your life easier rather than trying to plug in everything at once. Questions? We didn't get this. Does it make sense now? Okay, not blowing your brains? I asked before I started recording, I said, okay, any questions from yesterday? Because we kind of ended our session yesterday a little bit abruptly, didn't have a lot of time for questions, and they're like, We were just confused. All right, so any questions now that we've gone over it? Okay. All right, let's take a look at problem 14. And readeth problemo 14. Oh, let's see, who read the last one? Audrey? Can I read this one?
Two small spheres weighing 4.2 newtons each are tied to opposite ends of a string so that their centers are 1.32 meters apart. A slip knot is tied in the center of the string, making the spheres 0.5 meters apart. In this condition, they are thrown whirling into the air with an angular speed of 31 radians per second. While in the air, the slip knot comes untied. Calculate the new angular speed in radians per second.
All right, you know what ladder ball is? Little plastic ball or rubbery ball with a little piece of rope in between. You toss it, you try to land it on one of the rungs of the ladder and have it wrap around. Okay, this is like a 1 pound ball on either end and a full meter-long string between them. And I don't know what you're trying to loop this thing onto. It's like extreme ladder ball. Okay? Maybe you're like, chucking this thing and trying to lap it around like girders of a skyscraper being built. I don't know, whatever. Anyway, and it's really spinning fast. 31 radians per second. That's 5 complete spins in every second. This thing is really flying. But it's not 1.32 meters. They tie a knot in the middle so it brings them in closer. And then they're spun through the air. Again, smaller radius is going to be easier to spin them. But as you go through the air, the knot comes untied. Well, what's going to happen if the knot comes untied? They're going to spread back out as they're spinning. So because it spreads outward, what should we expect to happen? Slow down, because we're increasing the rotational inertia by spreading out. As it spreads out, remember the Holberman sphere yesterday, kind of got to see the spread out, slow spin, coming in close, much faster spin. So that's what's going to happen. We're going to expect it to slow down considerably when it spreads back out. But that's assuming there's negligible air resistance and nothing else to slow down the angular momentum. So here's where we should have used this equation. Is this the equation we used for conservation of angular momentum? All right, perfect. All right, so all we really need to know, the masses doesn't really matter because it's the same two spheres spinning through the air before and after, right? Same rope in between them. So the mass is negligible. And in both cases, it's just these particles spinning around and around, right? So we take the radius of the first spin and you say, ooh, I forgot to cut this distance between them, which would be a diameter, in half. You know the cool thing? The diameter is a double radius, right? And if you actually do a double radius and square it, that gives you a multiple of 4 on both sides, but the 4 cancels. So if you used the diameters, the actual distance between them, instead of the radii, the numbers work out the same. But, since we like to be accurate, technically, if they're 0.5 meters apart, what's the radius when they're first thrown, class? 0.25 meters. Technically is that radius. Again, if you used 0.5, the answer is still going to work out for you. And then the spin rate that they're initially thrown at, whirling through the air, 31 radians per second. Again, that's about 5 revolutions every second. And then the slip knot comes untied, and they're now 1.32 meters apart, which means the radius is 0.66 meters. And we'll square that. Again, if you plugged in the 1.32 and squared it, it's going to work out for you. And we find the new angular speed. And plug it in. And 0.25 squared times, not plus, times 31. And divide that by 0.66 squared. And it does indeed slow down considerably. What is the new angular speed or angular velocity or spin rate? Class? 4.447, or was it 366? Yes, so 4.45 radians per second. That's less than 1 spin per second. So, did we get this answer? All right, so this one we were good. You too. Audrey, question? All right, does it make sense now? All right, questions on this at all? All right, here in just a few minutes, we're going to take a quiz. Now, I've got a handout that we're going to go over to help drill over this math. Any questions on angular or rotational inertia, torque, angular momentum, rotational kinetic energy? Questions on any of that before we look at the handout? All right, well, let's take a look at the handout. Obviously, if you're watching on video, the handout is in the description of the video as usual. And at your seats, go ahead and work the first problem. Give you about a minute and a half head start, and then I will begin working it on the board. Check your work on the first problem. Did you use the equation L equals I omega? Angular momentum, L equals I omega. The I, though, is 3/10 mr squared. So I used 0.3 instead of 3/10. The mass I changed to kilograms, 0.011. And then the radius, well, diameter is 3.5 centimeters. Radius is 1.75 centimeters. Make it meters, 0.0175 meters. Of course, that gets squared. It gives you an incredibly tiny value, millionths of a kilogram per time meter squared. I put that tiny value, which I put in scientific notation, into the memory of the calculator. It's a little bitty top. It's not going to have a lot of resistance to spinning, so rotational inertia very small. The omega, it says, was 4 revolutions per second. Well, that's 8 pi radians per second. 8 pi, I mean, why would I get a decimal and make that harder than it needs to be? So I just wrote 8 pi up here. Took the memory value times 8 times pi, got 2.5 e negative 5. Notice the units, kilograms times meters squared per second. Anyone get that answer? Questions? Comments? What were we doing wrong? Where were our mistakes?
I didn't change to meters, and I used 8 pi over 60 seconds instead. Oh, you treat it like 4 revolutions per minute instead of 4 revolutions per second. Okay, that would do it to you. Okay, so forgot to change to meters. We're so used to RPMs, just assume revolutions per minute, and so divided by 60. Okay, easy mistakes to make. All right, any other questions, comments? All right, go to the keeping some of these numbers maybe in the memory
because we're using the same top in the next box. So, next box. All right, questions on the torque. Questions on the torque. It says find the torque needed to accelerate. So I know my formula is going to be tau equals I alpha. And I haven't talked about torque and acceleration in the same breath, right? So I already know the I. I told you, save that memory value. I still have that in the memory. I'm good with that. Or maybe you had to edit it, right? If we actually forgot meters in the last one. But we get that value. That's our I value. For the alpha, it says it's accelerating from rest to 4 revolutions per second. So the change here is a change of 8 radians per second in a time of, it says, 0.25 seconds. So I took the 8 pi divided by the 0.25, got 100 radians per second squared, basically. Multiply that by the memory value to get 1.0 rounded, e negative 4 Newton meters. Did we get this for the torque? Questions? Comments? Where did we go wrong? Give me some feedback here.
Multiplied by the radius. Again, I don't know why.
Instead of radius squared.
Yeah.
Okay. All right, so remember MR squared for that I value.
I didn't have the right memory.
Oh, okay. So you got the 100.53 whatever, and you plugged in a memory, but it was the wrong value in the memory.
Yeah, but I had the same numbers, it's just not to the right power. Or not to the
Okay, so probably had these maybe still in grams or still in centimeters or something then. If it's the right digits, just in the wrong exponent or power of 10, that's probably what happened. Okay? Other comments?
I went with the wrong formula at first. I did the force.
Yeah, the only problem is we don't know any force, right? So we can't do it if we, so that's how you tell the difference. If it talks about how much force is applied and talks about a distance from the pivot, then use FR. If it's, anytime it mentions acceleration, though, that's your giveaway for the tau equals I alpha. All right? Yeah, any other questions on the first part? All right, go to the second part now, finding the rotational kinetic energy. Do you have the correct I value yet, Audrey?
Yes.
Okay, just making sure, because if I say
Yeah.
if you keep using the wrong memory value, it's going to keep messing you up, right? So that rotational inertia number, if you caught on, very, very important to get correct. Got to get that I value correct, because everything else seems to use that I value. Because again, that's what defines how easy it is or is not to spin or change the spin. Real quick note here, for some of you, you may need to actually figure out what 8 pi is and then square it.
That's what I did wrong, because I had everything right.
Yeah, so if you started here, you'd, okay, what's 8 times pi? Square that, then multiply the memory, then take half. Might be the better way to go. I didn't think of that. I started with 0.5 times memory, like, oh shoot, now what? So I did times 8 squared times pi squared, since technically they were both being squared. But the best way would be 8 times pi, square it, that's actually following order of operations, and then times memory times 0.5. Do we have it now? All right, Michael, questions, comments?
I'm getting the wrong E value.
And you have corrected your memory now?
Yes.
Okay, so this is correct.
It's E negative 5.
Okay, so a half times the memory times the 8 pi squared. Now your calculator is different. I think you could do parentheses around the 8 pi.
I'm doing that.
Oh, you're squaring the pi. You're not squaring the 8 and the pi.
Okay.
There it is. Okay, that's why. All right. Problem solved. Okay, questions on that? All right, go on to the next problem here with the solid sphere. Picture bowling ball, I guess. did we get the correct I value? The 0.0305, or maybe you did like I did scientific notation, 3.05, blah, 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 -2. All right, did we get the correct omega, 33.3 repeating radians per second? Did we plug it in correctly and get the correct energy? All right, ladies are nodding. Michael is finishing up. Question, comment, Michael. Did you figure out what you did wrong? If you missed something, are you good?
No,
No, not good.
I have all the numbers correct, but
So these two numbers are correct, okay? And then as far as plugging it in here, I decided to break it into pieces. I said, let me just find this first part first. So I did a half mv squared, so half 5.34 squared. I got 42.4. And I said, okay, now let me take half of the memory 1 and the memory 2 squared, and I got the 16.96. Since they both worked out to easy numbers, I went ahead and just added them and got this, since they weren't weird where I needed to put them in a memory or anything. So maybe you forgot to square perhaps some values. That's a common mistake.
the omega is 33.3.
Right, 33.3 repeating.
Okay.
So coming over here, we'll square that to get a big number around, 1,000-ish. Multiply that by this little bitty number, and then take half of it. That is your rotational kinetic energy.
I forgot to take that.
Ah, okay. So your answer was 74, 75, 76? Okay, so that's it. You just forgot the 1/2 right here then. Okay? All right. Questions, comments? Got it? All right. And the last problem. It looks like we're all good to go here. We didn't end up using the mass, did we? Mass of 75 grams. No, we could have, right? Technically, this is based on the fact that angular momentum, L, is conserved, which means that I, omega, is conserved. And so we could have found I taking mr squared, because it's a revolving particle. We could have done that. So we could have multiplied the 75 on both sides. But the 0.075 gram or kilograms would have canceled anyway. So that's why I just started here, ignore the mass. It doesn't actually affect anything. Do you want to make sure we convert to radians per second? Now, if we left the 2 revolutions per second, your answer would come to about 10 revolutions per second. So it's spinning around twice in a second. By the time the string shortens wrapping around the finger, it'll be up to about 10 revolutions per second. But we want radians per second, and we get that answer there. It seems like we're all good to go on that. All right, now you've got a break, I think. It could be a break in that we don't have enough time to take the quiz today. Hopefully, you use your time over the weekend wisely, because that means the quiz will be on Tuesday when we come back. What you can do over the weekend, maybe on Monday evening, when you start panicking about the quiz, is go to YouTube, print yourself out a new copy, or even just bring it up on the screen, because again, the handout is in the description of the video. Bring that handout up so you don't have the answers on it already. Try to rework the problems. And then compare that to your answers on this, because you should have all the correct answers copied down now. If you're not getting the correct answer, you can find the part of the video in which I go over it again. Study your terms, study your formulas, study your units, and then of course the math is reviewed here. So if you use your time well, maybe it's a break that we don't have to take the quiz today. If you don't look at it at all over the 3-day weekend, though, it's very bad news to have a Tuesday quiz after a 3-day weekend. Your only other homework is to study over pages 200 and 203. There's some example problems I want you to look over so you're prepared for what we will talk about after the quiz in our next lesson. All right? So again, homework is be ready for the quiz, which we were supposed to take today, but we only have 5 minutes left, so we're not taking the quiz today. And study over pages 200 and 203 in preparation for what will be coming in our next lesson. All right? Have a wonderful 3-day weekend.